We've been taught. Oh, the title, by the way, more C of M. What do you think C of M stands for? Sorry? Conservation of momentum. Conservation of momentum. Here we go. We've been talking about crumple zones and how the key to minimizing injury in a car accident is to increase the time of collision. If I can increase the time of collision, what does that lower? Yeah, because impulse, which we're stuck with in a collision for a single car, is force times time. So if I can increase time, force gets small. What about for something like a smart car where there's just not much room to make a crumple zone? The engineers thought of that, and what they did is they turned the engine into the crumple zone. Put your pencils down, look up. Toilet paper physics. What? Our school has those big toilet paper rolls, those big ones. You may have noticed that if you pull very slowly, the roll will spin. But if you pull quickly, what happens instead? Oh, come on, you must have noticed this. The paper tears. Why is it that in one situation I can make the roll spin, and in the other situation I can tear the paper? Shouldn't it be the same result no matter what? I'm trying to mess with you in all possible situations. Hopefully you'll never look at toilet paper rolls the same way again as well. Put your pencils down and look up. We're going to break collisions into two main types. There are two main types of collisions. There are collisions where objects bounce off of each other after the collision. For example, when curling rocks collide, when billiard balls collide. A hockey body check where you don't wrap the person up, where you just body check them. Baseball and a bat is a great example. I've never seen a baseball stick to the bat. They always bounce off of each other. Some car crashes. There are some car crashes where the wreckage doesn't stick together. There is some car crashes where the wreckage does stick together, but some car crashes, the objects come apart. We have a fancy name for that. If the objects bounce off of each other after the collision, we call that an elastic collision. There are also, some collisions where the objects do stick together. For example, when a football player wraps up and holds onto a person that they're tackling. Dart hitting a dartboard is a good example because the dart sticks into the dartboard, ideally, unless it falls because you don't know how to play darts. Some car crashes, there are some crashes where the wreckage does stick together. A bullet entering and sticking a target, as long as it doesn't go all the way through the target. These type of collisions we call inelastic collisions. You're going to need to know both of these words. I'm not going to ask you to define them, but I will, for now, say something like two objects collide inelastically. And what I've just told you is after the collision, they stuck together. Or I'll say two objects collide elastically. What I've just told you is after the collision, they came apart. How can you remember which is which? I always, even to this day, think elastic band, rubber bounces apart. Elastic, rubber, bounce apart. Inelastic isn't rubber, doesn't bounce apart. What's the opposite of doesn't bounce apart? Sticks together. There's a bit of a problem here as well, because if I say there was a collision and it was an elastic collision, it's tough to tell whether I just said it was an elastic collision or whether I said it was inelastic collision and just didn't say the or the an. So what I will almost always try and do, Phil, is I'll exaggerate it. I'll say there was a collision and it was an inelastic collision. I'll do a big pause so you can clearly see where the and started and then the next word starts, so it's pretty obvious. So it's not, I'll do that even without thinking about it, because otherwise if I say there was an elastic collision, it's tough to see which one I meant right there. Okay? Elastic and inelastic. Let's look at some collision examples. Okay. I'm going to show you several different collisions. Somebody in the hallway there? Okay. The first one I'm going to show you two videos of an explosion. It's not going to be a big explosion. It's two little carts that have been pushed together by springs. In one of the explosions, both masses are identical. In one of the explosions, one mass is heavier than the other mass, and your job is to try and figure out which one is which. So here's the first video.
Unequal mass exploded.
That's what I mean by explosion. Here's the second video.
Equal masses. Explosion.
In one of those, both masses were identical. In one of those, one mass was heavier than the other. And your job is to try and figure out which one's which. Here's the first video again.
Unequal mass exploded.
Let's watch that again.
Unequal mass
Are both these masses
exploded.
identical, or is one heavier than the other? What do you think? Jess? Why? You're right. What? Oh, first of all, before the collision, right now, what's the momentum of this object? So I said collision, explosion. What's the momentum after the explosion? Still. So they're going to fly off with the same momentum. If one has a bigger mass, it must have a smaller velocity.
Unequal
Which one
mass
is heavier, the left
exploded.
mass or the right mass? Watch, watch, watch. Which one's heavier, left mass or right mass? Left-hand mass, because it was traveling slower. Right-hand mass was going faster. They both had the same momentum. Okay, kind of see what we're getting at here? So now I'm going to show you 3 collisions in a row. One of the collisions is going to be identical mass colliding into identical mass. One of the collisions is going to be a heavy mass hitting a light mass, and one of the collisions is going to be a light mass hitting a heavy mass. Your job is to try and figure out which one is which. So here's the first collision.
Elastic, big mass and small mass.
By the way,
Elastic,
this collision
big
here,
mass and
elastic
small
or
mass.
inelastic? Elastic. Okay, so now I'm going to show you 3 elastic collisions in a row. One is going to be same mass hitting same mass. One is going to be heavy hitting light. One is going to be light hitting heavy. Our job is to figure out which is which. So here's the first one.
Elastic, big mass and small mass.
Here's the second one.
Elastic, small mass hits big mass.
And here's the third one.
Elastic.
Any guesses? Any of those look different from the other two or stand out? Brennan. Which one? First one, second one, third? Second one? Hang on, second one. Let me look. That was video 4.
Elastic, small mass hits big mass.
Same mass hitting same mass, heavy mass hitting light mass hitting heavy mass.
Elastic, small mass hits big mass.
Light hitting heavy, convince me. First of all, momentum has to be conserved. If it was the same mass hitting the same mass and it was perfect, this isn't quite perfect. There's some friction, there's some outside forces, but if it was perfect, the first mass would come to a stop and pass all of its momentum to the second mass. You know what that one was? I think that was the third video, video number 5. I think this is same mass hitting same mass. That's pretty close. Also, I noticed the velocity that the second mass left at was really close to the velocity that the first one came in at. Now, Jess is saying the second video is light hitting heavy,
Elastic
that means
small
that we
mass
should
and
see
big
the second
mass.
mass move off way slower than the first mass came in on. Same momentum
Elastic
transfer,
small mass hits big mass.
but bigger mass, smaller v. And so that means that the first one should be heavy hitting light. We should see the
Elastic,
first mass,
big mass, and
second
small
mass, sorry,
mass.
take off faster than the first mass came in. Is Jesse right? Jess is on a roll. Well done. 3 more collisions. Again, same idea. One of them is going to be same hitting same. One of them is going to be heavy hitting light. One of them is going to be light hitting heavy.
An elastic, big mass hits small mass.
Elastic or inelastic collision? Inelastic stuck together? Okay, now I'll watch all 3.
An elastic,
Here's the
big
first one.
mass hits small mass.
Here's the second one.
An elastic, small mass hits big mass.
Here's the third one.
Inelastic.
Any of those stand out? Yeah? Which one? Oh, I thought you said yeah. Sorry. First one again.
An elastic, big mass hits small mass.
Second one again. Well, that was anticlimactic. Second one again.
An elastic, small mass hits big mass.
That one looks interesting to me. That one to me looks a bit different from the other ones.
An elastic, small mass hits big mass.
Levy. Light hitting heavy? What's your rationale? You're right. Convince me. And it passed its momentum over, but there was so much extra mass that even though you passed the same amount of momentum over, big mass, small v. The other two, it's a bit trickier. I think the other two, the first one is heavy hitting light, and I think the last one is same hitting same, but it's a bit trickier. You really got to watch. Okay. Let's do some examples. I like example 1. I like example 1. Example 1 is a nice question. A car traveling at 44 meters per second collides head-on with another car traveling in the opposite direction. This is going to be important. If the cars stick together on impact, what's the velocity of the wreckage immediately after the impact? Ty, what does this want me to find? Final velocity. Is there a collision in this question, Ty? Is there more than one object? This is a job for conservation of momentum. Before I start, though, I'm going to be lazy but organized. Ty, is there more than one mass in this question? A, B. You can write, Mateo, if you want to, let the 1.5 times 10 to the 3 kilogram car be mass A, or if you just put a letter above it in the question, I'll figure it out. Next thing, Ty, is there 2 different directions in this question? So we need to let one of these be positive and one of these be, which one you want to let be positive? This 44, you want it to be positive or negative? I don't care. So let's put a plus sign there. What does that make this 22? Let's put a negative there, and I think we've taken care of any sloppy mistakes. Is there a collision? Is there more than one object? This is a job for conservation of momentum. The sum of all the momentum we start with equals the sum of all the momentum we finish with. Ty, before the collision, what's moving? Mass A, mass B, both or neither? Before the collision, stuck together or separate? I guess if they're going in opposite directions, they have to be separate. So, momentum is what times what? It's on your green sheet. P equals. So, momentum is what times what? Say it again. So, you're telling me I have these two moving. It's going to look like this. The mass of car A, velocity of car A before we start, plus mass of car B, velocity of car B before we start. I think that's the total momentum that we have initially. You okay with that? Good. Bam! They collide. After the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? Now here I said stuck together, or I could have said collide inelastically, and I would expect you to clue in they stuck together. In fact, at the bottom of the page where it says, is this collision elastic or inelastic? This is definitely what kind of a collision? So I'm lazy. I'm just going to circle the word inelastic. How will I write that? It's going to be the mass of car A plus the mass of car B in brackets V final. Ty, what did you say we're trying to find? Are you lazy but organized? Say yes. Is that too much? Or we would all realize the bracket is multiplying, so we'll divide it over. I didn't feel like rewriting the whole equation just for that. On the next line, though, I am going to write the VF on the left side where I like to see it. And I think I can plug and chug now. What was mass A? And we cleverly labeled it lazily but organized, so we don't have to think. By the way, 1.5 times 10 to the 3, that's 1,500, which is less writing. What was velocity of car A initially? Plus, what was the mass of car B? Hey, you did the conversion in your head. I'm impressed. What was the velocity initially of car B? Negative, you say. Are they going in opposite directions? Oh, okay, I agree with that. Divided by 1,500 plus 1,000. I think this will work out to like a nice decimal. I don't think it's going to be a yucky, repeating, blah, blah decimal. Because you do adding by 2,500, and that usually works out nicely. Again, as always, I would encourage you to practice typing these into your calculator. Kiefer, I would actually also recommend don't use your pencil eraser to type. It actually wears out the buttons, the ink from the buttons faster, and you're far more likely to hit a key and not have it register and not catch it because you're not touching the keyboard directly. You don't. I mean, you're fine if you do that, but for what it's worth, if I'm really paranoid, type with my fingers. What'd you get? Negative 17.6? Which one, negative or positive? So which car is the winning direction? Car A or car B? Okay, so 17.6 meters per second. I should have included easts and wests in here. I just said in the opposite direction. If you wanted to include a direction in the direction of car A. If I model this collision, then, here's what it looks like happened. A big car going fast did a head-on collision with a smaller car going less fast. Wham, they collide, and they stuck together, and they moved off in this direction. So it looked like this. Which car do you think, which passengers do you think had more damage? Car A or car B? I think car B, because there was a bigger acceleration if we ran the numbers. And as I said before, it's not impulse that causes damage. It's not even force that causes damage. It's acceleration. Everything comes down to that. I like example 2. I like example 2. Example 2 is a nice question. Annika, you do any curling?
No.
Curling is a lovely example of conservation of momentum because the ice is nearly frictionless. The collisions are great. The only problem is in real curling, all the rocks have the same mass, which would mean the mass would cancel out of all our equations. So I will always have the rocks be different masses, even though that's not how curling works. But curling. A curling stone is traveling due east. It strikes another stone that's moving east. After the collision, the first stone is moving east. What's the final velocity, magnitude, and direction of the second stone? Annika, is there a collision here?
Yeah.
It even says after the collision. Is there more than one object? I'm going to use conservation momentum. I'm going to be organized and lazy. Is there more than one mass?
Yeah.
Mass A, mass B. I see direction. I see east. Do you want to let east be positive or negative? I don't care.
Positive.
Are you positive? So I'm going to put a plus sign there. This 1.2, positive or negative?
Positive.
What about this 0.65?
Positive.
I've taken care of that. Had there been any wests, those would be negative. And now I could really relax and say, as long as I'm careful, I've taken care of any substitution issues. This is a job for conservation of momentum. The total or the sum of the momentum that we started with equals the total or the sum of the momentum that we finished with. Before the collision, what's moving? Mass A, mass B, both or neither?
Both.
Stuck together or separate?
Separate.
Mass A, velocity A initial, and mass B, velocity B initial. That's how much momentum we started with. That's also how much momentum we'll finish with. Wham! They collide. You awake now? Every collision, Mr. Dueck? Oh, wait till we get to the explosions. After the collision, what's moving? Mass A, mass B, both or neither?
Both.
And I think separate.
Yeah.
Now, how can I assume separate? Well, they gave me the velocity of A, and they want me to find V final. If they were stuck together, that would mean that they gave me the answer, which would be a silly question, because the answer would be 0.65. Okay, so I'm going to have mass A, V, A final, plus mass B, V, B final. Annika, what are they asking me to find?
They're asking you to find the final velocity of B.
That guy. This is going to drop down. The left-hand side is going to drop down like a domino, yes?
Yep.
M-A-V-A initial plus M-B-V-B initial. Then what?
Sorry, it's catching up to you.
Yep. Take your time.
Then divided, or no, subtracted by...
Reverse bed mass. First, we're going to move this term over by going minus M-A-V-A final. Then...
And then divided by M.
Yep. And this is going to be the final velocity of B. Before we start crunching numbers, I'm going to make a prediction because I'm going to model this. Look up. Sorry for those of you on YouTube who can't see that I'm modeling a collision. It looks like we have two curling rocks going in the same direction. Rock A is in the back and going faster. It rear ends rock B. What happens to rock A's speed after the collision? Does it speed up or slow down? Look at the numbers. What happens to rock A? Did rock A speed up or slow down? So did rock A gain momentum or lose momentum? It must have lost momentum. So what must have happened to rock B? It must have gained momentum. Did it gain mass? Then it must have gained velocity. How fast was rock B going before the collision? I can tell you before doing anything that we're going to get an answer bigger than 1.2. So there's a bit of a built-in error check. If I visualize the collision, I can at least tell you after the collision whether we sped up or slowed down quite often by just looking at who gained momentum, who lost momentum, really by looking at the velocities, because we're not going to be dealing with a changing mass. All right, let's plug and chug, being very careful with negatives and positives here. Annika, mass A, was it 18?
Yep.
Velocity A initial
2.6.
plus mass B 12.5.
Yep.
Velocity B initial
1.2.
positive.
Positive.
Okay. Minus 18. Velocity A final,
Yeah, 0.65.
0.65. That's also in the positive direction still?
Yes.
Okay. I could have, by the way, had rock A bounce backwards off, and then it would be heading west, and we would have called that negative. I didn't go that far. All over 12.5. I'm telling you the answer is bigger than 1.2. I hope. I didn't do this one in my head. I'm going from memory. I think this almost works out evenly, but not quite. I think it works out. Does it work out to like something 0.01 or something like that? 4.01, I think, maybe. Mateo's nodding. Now I'm nervous. Oh, I got a couple more confirmations. 4.01. Mateo, positive on your calculator or negative on your calculator? So what direction did we let be positive in the original question? And I think I did say find the final velocity, and I think I wrote in brackets magnitude and direction in the instructions, did I not? So we're going to be fussy here and put the east. Is this collision elastic or inelastic? Rubber band bounced apart. Okay. Example 3 is the last question of the lesson. I'm going to save this for Thursday as a brushing the cobwebs, jog your memory. I'm going to do example 3 on Thursday, and that's going to be it. The rest of the class on Thursday is going to be yours to work. The homework is going to be every question from this lesson, so you can technically probably do all of them, or at least start them. There's going to be some that are tricky. You also have homework from last day as well. And you also need to remind me, this is for Brendan, him and I have been chatting. I have to show you the real definition of momentum video. I've lied to you. Momentum is not mass times velocity. It's only mass times velocity if you're not going near the speed of light. But of course, there's an Einstein version as well that supersedes the one that I'm giving you. So you have the remainder of class to work on the homework.